Hi everyone, so today we're going to talk about a couple of really interesting things in elementary number theory, and they are the LTE Lemma and P-adic valuations. Now LTE stands for lifting the exponent, so we are going to study what this lifting the exponent lemma is, what this concept of this P-adic valuation is, and these are a couple of really interesting areas in number theory, like I said, and they have a lot of research applications as well. P-adic valuations, P-adic metrics is being studied quite a bit in the research arena. So if you're really interested in these areas, you might want to check it out. But I'm going to explain to you what these concepts are a little bit in brief, and then we're going to see how we can apply this to a problem and what's really the practical application, the practical interpretation of these two concepts. So let's just get right into it. This is the problem number 11 from the AIME in the year 2020. And in this video, we're going to talk about lifting the exponent lemma, P-adic valuations. Most of our discussion is going to be spread around that area. Then we have book sessions for the AIME, and at the end, this is the problem number 11.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so the question says that let n be the least positive integer such that this given quantity divides 149 raised to power n minus 2 raised to power n, and then we need to find the number of divisors of n. So n is the least positive integer. It's the minimal integer in a way. So we kind of need to consider the minimalistic cases. Now, before we really dive into this problem, and I'll demonstrate you a pretty cool way of solving this. Before we really go into that, let me just give you an introduction to what this LTE is and what this P-adic valuation is. So let's maybe define certain things. Let's use a little bit of notation, right? So maybe let's write down a couple of definitions. So define the P-adic valuation of n. So when I say P-adic valuation of n, it is in a way noted like this. It is defined by this. This is the notation, and this essentially means the P-adic valuation of n, right? So that's how I would be writing this. Okay, great. So define Vp of n to be the P-adic valuation of n, right? And what is this P-adic valuation of n? So P-adic valuation of n is nothing but a number k such that p raised per k divides n, but p raised per k plus 1 does not divide n. So let's maybe just take a general example. So let's say we have a number n, like we're considering over here, and that natural number n, let's just write its prime factorization. Using the fundamental theorem of arithmetic, we can write down its prime factorization as, let's say, p raised power a, p1 raised power alpha 1, p2 raised power alpha 2. This goes all the way up till, let's say, pm raised to the power alpha m. Okay, great. So what is the P-adic valuation of n? It would be a, right? It is essentially a number k such that p raised per k divides n, but p raised per k plus 1 does not divide n. So it's clear to see over here that p raised per a plus 1 does not divide n. But really, are you getting the feel of this P-adic valuation? Well, you might not, but when I say this next statement, it will be much easier to understand. So P-adic valuation, right? It is nothing but the highest power of this prime p that divides n. As simple as that. I repeat, it's the highest power or the largest power of this prime p that divides n. Right? So over here it is a. It's clear to see that p raised per a plus 1 does not divide n because prime factorization is that way. So the P-adic valuation of n will be a. Now let's just maybe take a practical example. So for example, we have 147 in the question. Let's maybe look at 147. Now the prime factorization of 147 is, I believe, 7 squared times 3. 49 times 3 is 147. Now if I ask you a question, what is the P-adic valuation of 147? What does this mean? What is the interpretation of this? Well, the interpretation is very clear. It is the highest power of 3 that divides 147. I repeat, the highest power of 3 that divides 147, and it's clear to see that that is equal to 1. Similarly, if I ask what's the 7-adic valuation of 147, well, you will say it's the highest power of 7 that divides 147. So it's the highest power of 7 that divides 147. That's clear to see it is equal to 2. So it's really as simple as that. You just need to understand the interpretation and its application for problem solving, right? It is really the highest power of this prime p that is dividing this natural number n, and it is nothing more than that. Okay, it's a very simple concept at the core of it, right? Okay, great. So now that you kind of have this understanding of this p-adic valuation, essentially the highest power of the prime p that divides n, keep in mind that 3 and 7 over here both are primes, and over here I'm specifically referring to primes. 2 as well is involved, okay? So now that we know what this p-adic valuation is, let's talk about the LTE lemma, right? LTE lemma, LTE theorem. So LTE, like I said, stands for lifting the exponent lemma, okay? And it essentially states that let p be a prime, like we were considering before as well, and x comma y are integers and n is a natural number, okay? And suppose that the prime p divides x minus y, but p does not divide x and p does not divide y. So it's a couple of conditions over here. The prime p must divide the difference of x minus y, but individually it can neither divide x nor can it divide y. And in such conditions, then we have the p-adic valuation of x raised to power n minus y raised to power n is equal to the p-adic valuation of x minus y plus the p-adic valuation of n. So essentially what I'm trying to say is the highest power of this prime p that divides x raised to power n minus y raised to power n is the highest power of this prime p that divides x minus y plus the highest power of this prime p that divides n. And the interesting thing to keep in mind is that p is odd, right? P over here is odd. This formula only works for odd primes. So for example, p is equal to 3, 5, 7, 11, 13, 17, 19 and so on and so forth. Odd prime. Well, then you might ask the question, what if it's an even prime? And well, there's only one even prime, it is equal to 2. So let's just consider that as a separate case. If p is equal to 2 and n is equal to even, n is an even number, then we have the 2-adic valuation, because here p is equal to 2 of x raised to power n minus y raised to power n, and this simply becomes 2-adic valuation of x minus y, right, plus the 2-adic valuation of x plus y plus the 2-adic valuation of n minus 1, right? So these are two interesting things that you should probably keep in mind, and this lemma is called as lifting the exponent lemma. Now, I've talked about this thing called as Zygmundi's theorem in a couple of my questions before, and if you actually see, Zygmundi's theorem is nothing but a simplified version, you can say, of this LTE lemma. So you can use LTE lemma basically wherever Zygmundi's theorem or Zygmundi's lemma was used. So LTE lemma is really a more generalized, a more rigorous version you can call of lifting the exponent lemma, right? So now that we kind of know what this p-adic valuation is, now that we know what this LTE lemma is, what this interpretation of this LTE lemma is, let's maybe just jump back into the question, right? So in the question they've given us this condition, right, that 3 cube times 5 raised to power 5 times 7 raised to power 7, pretty nice symmetry over here, isn't it? Divides 149 raised to power n minus 2 raised to power n, and we need to find the minimal n that satisfies this condition, blah blah blah. Okay, now what I'm going to do is I'm going to apply LTE lemma. So if you remember, we had x raised to power n minus y raised to power n. So if I really let x equal to 149 and y is equal to 2, I can calculate certain things. And I'm going to do it in 3 ways. First, I'm going to consider the prime 3, then the prime 5, then the prime 7. Because we have primes, well, that's kind of direct hint to use LTE lemma. Because LTE lemma, like I said, can only be used for primes. Right? P-adic valuation, P is a prime, right? So from LTE, I can say that the 3-adic valuation of 149 raised to power n minus 2 raised to power n, this is equal to 3-adic valuation of 149 minus 2 plus the 3-adic valuation of n. Right? Now, just to remind you, what will be this 3-adic valuation of 149 minus 2, which is 147? It is the highest power of this prime p that divides 147. And like I said before, 147 is 7 squared times 3. We've discussed this like a few minutes ago. So the highest power of 3 that divides 147 is equal to 1. So this simply is 1. So the 3-adic valuation of 149 raised to power n minus 2 raised to power n is actually equal to 1 plus the 3-adic valuation of n. Now, here's the interesting thing. If you actually notice over here, 3 cubed divides this given quantity on the right hand side, right? So can I say that the 3-adic valuation of 149 raised to power n minus 2 raised to power n will at least be 3? it'll at least be this quantity 3. Why? Because 3 cube divides that quantity, right? 3 cube divides that quantity. So the highest power of 3 that needs to divide this must be at least 3, because we know that 3 cube divides it. So maybe 3 raised to the power 4 divides it, maybe 3 raised to the power 5 also divides it, but at least in the minimalistic condition we can say at least the highest power of 3 that divides this quantity is 3 at the very least, because 3 cube divides this 149 raised to the power n minus 2 raised to the power n. So effectively 1 plus 3-adic valuation of n is essentially greater than or equal to 3, or I can state that the 3-adic valuation of n is greater than or equal to 2. Now let's come back to the interpretation of a p-adic valuation. What does this mean? This means that the highest power of 3 that divides n is at least 2. Highest power of 3 that divides n is at the very least 2. So 3 squares divides n at the very least, and I'm going to mark that as number 1. This is obviously considering minimalistic conditions. Maybe 3 cube divides n, maybe 3 raised to the power 4 divides it, but we do not know that yet. What we do know, however, is that 3 squared divides n. Okay, amazing. Now what I'm going to do is I'm going to consider 7-adic valuation of 149 raised to the power n minus 2 raised to the power n. This just becomes the 7-adic valuation of 147 plus the 7-adic valuation of n. Now 7-adic valuation of 147, highest power of this prime 7 that divides 147. We've seen it before, it is actually equal to 2. So 2 plus 7-adic valuation of n is the 7-adic valuation of 149 raised to the power n minus 2 raised to the power n. Now again, why did I consider 7? Well, it's just in the question, guys. I'm going to consider 3, I'm going to consider 7, I'm going to consider 5. So the next number that I'm going to take is going to be 5. So just giving you a brief into to what's going to come. But the highest power of 7 that divides this quantity over here is actually equal to 7. And again, we're just considering minimalistic cases. So therefore, V7 or the 7-adic valuation of 149 raised to the power n minus 2 raised to the power n needs to be at least greater than or equal to 7, right? So 2 plus 7-adic valuation of n needs to be greater than or equal to 7, or basically 7-adic valuation of n needs to be greater than or equal to 5. That means that the highest power of this prime 7 that divides n is at the very least 5. So at the very least 7 raised to the power 5 needs to divide n, and that is our condition number 2. So we've really received two conditions: 3 squared divides n and 7 raised to the power 5 divides n. Now, like I said a couple of seconds ago, I'm going to consider 5 now, but there's an issue. There's an issue with 5. Well, if you see the lifting the exponent lemma, there was a condition that this prime p needs to divide x minus y. Now, over here, x is 149, y is 2. This is what we've been considering all along, right? And now I'm saying that I want to use the prime p, but from LTE we know that the prime p must divide x minus y. But that's the problem. 5 does not divide 149 minus 2. 5 does not divide 147. Earlier, 3 divides 147, 7 divides 147. So it was good till there. But 5 does not divide 147. And that is my problem over here. So over here, we're going to have to be a little bit smarter. So the problem solvers, the problem curators rather, have to trick us a little bit over here. But we are actually a little bit smarter than them, aren't we? Right? So we cannot directly apply LTE over here, but we can modify it in a way so that we can apply LTE. We're going to use a little bit of modification. So now, let's just see our original condition. So this is our original condition, right? Okay. So we know that 5 raised to the power 5 must divide this quantity on the right hand side. So at the very least, 5 must also divide this quantity on the right hand side. Essentially, what I'm just trying to say is that 149 raised to the power n minus 2 raised to the power n needs to be at least congruent to 0 mod 5. I know it's divisible by 5 raised to the power 5, but at the very least, we know it's 0 mod 5. Okay, great. Now, well, 149 is obviously minus 1 mod 5, right? So this quantity essentially reduces to minus 1 raised to the power n, minus 2 raised to the power n is congruent to 0 mod 5. Now, here's the thing. This is not 0 mod 5 for all values of n. And I'll just demonstrate that to you very quickly. So let's say we have n. We're going to make a table of values between n, and then we're going to calculate minus 1 raised to the power n, minus 2 raised to the power n mod 5. So if I take n is equal to, let's say, 0, I'll get 1 minus 1, which is mod 5, which is obviously 0 mod 5. If I take n is equal to 1, I'll get minus 1 minus 2, which is minus 3 mod 5. If I take n is equal to 2, I'll get again minus 3 mod 5, 1 minus 4. If I take n is equal to 3, I'll get minus 9 mod 5, but that's simply really 1 mod 5. If I take n is equal to 4, however, I'll get 0 mod 5. And this pattern will keep on repeating. So what I'm going to see is I'm getting 0 mod 5, which I need. Mind you, I need 0 mod 5 over here, and I'm only getting 0 mod 5 at 0, 4, 8, and so on and so forth. So therefore n needs to be 4k to get minus 1 raised power n minus 2 raised power n is congruent to 0 mod 5, which is what we need. Or in other words, 149 raised power n minus 2 raised power n is congruent to 0 mod 5. So to get this, n must be equal to 4k, or in other words, 4 must divide n. So now, knowing this knowledge that n is equal to 4k, and then we have the divisibility by 5, now we can actually use P-adic valuation and LTE lemma in a slightly different way. So I'm going to write the 5-adic valuation of 149 raised to the power 4 raised to power n by 4. So you still get 149 raised to power n minus 2 raised to power 4 whole raised to power n by 4. So again, you're getting 2 raised to power n. But this is going to be equal to the 5-adic valuation of 149 raised to power 4 minus 2 raised to power 4 plus the 5-adic valuation of n by 4. So do you actually see what I did over here? Instead of directly taking 149 minus 2, I took 149 raised to power 4 minus 2 raised to power 4 because I know that is divisible by 5. Like I just told, right? N has to be divisible by 4. 4 has to divide n. So therefore, we raised it to the power 4, and now we know as a fact that 5 must divide it because we had 0 mod 5 over here. Okay, amazing. So we know for a fact that 5 divides 149 raised to power 4 minus 2 raised to power 4. But what does this 5-adic valuation really mean? This 5-adic valuation, it means the highest power of 5 that divides this quantity. So we need to actually see if 5 square, 5 cube, and so on and so forth divide it. So let's maybe reduce 149 raised to power 4 minus 2 raised to power 4 modulo 25. Or in other words, just find the remainder when 149 raised to power 4 minus 2 raised to power 4 is divided by 25. And that's really easy to do because again, 149 is actually congruent to minus 1 mod 25. So this just becomes minus 1 raised to power 4 minus 16 mod 25, which is actually equal to negative 15 mod 25. So the remainder is actually negative 15. It is not 0. So therefore, 5 square, which is 25, does not divide 149 raised to the power 4 minus 2 raised to the power 4. Therefore, the 5-adic valuation of 149 raised to the power 4 minus 2 raised to the power 4 is equal to 1. Because 1 is indeed the highest power of 5 that divides the given quantity, right? So basically, this entire thing over here becomes 1. So 1 plus the 5-adic valuation of n by 4 becomes the thing that we had on the left hand side, and really that's just the 5-adic valuation of 149 raised to the power n minus 2 raised to the power n. Okay, because these 4 and 4 just cancel, and simply 4 and 4 gets cancelled over here. But again, what did we have in our original question? So where did it go? Over here. Yeah, so 5 raised to the power 5 divides this quantity, so that means at least 5 must be the minimal power of 5 that divides the given quantity. So therefore I can state that the 5-adic valuation of 149 raised to the power n minus 2 raised to the power n must at the very least be greater than or equal to 5, right? Because that's essentially what we had in our given question, right? So 1 plus the 5-adic valuation of n by 4, this needs to be greater than or equal to 5, or in other words, the 5-adic valuation of n by 4 needs to be greater than or equal to 4. Well, what does this mean? The highest power of 5 that divides n by 4 is equal to 4. So in a way, 5 raised to the power 4 must divide n by 4 at the very least. Or if I just multiply by 4, I know that 4, which is 2 squared times 5 raised to the power 4, must divide n, and that is my condition number 3. So we've really reduced our given question down to 3 conditions. And let me just write down the 3 conditions once again. So first we have received the 3 square divides n, which was our condition number 1. Condition number 2 was 7 raised to the power 5 divides n, condition number 2. And the third one is obviously 2 squared times 5 raised to the power 4 divides n, that is condition number 3. Now if I just combine these 3 conditions, I will get 3 squared times 7 raised to the power 5 times 2 squared times 5 raised to the power 4 divided n. But we need to find the least n. We find the least n that satisfies this given condition. Therefore, the least value of n is indeed 3 squared times 2 squared times 7 raised to the power 5 times 5 raised to the power 4. So this is the least n that satisfies this given divisibility condition. So therefore, the divisors of n. What were the divisors of n? Well, it's just a standard formula. I'm sure you've seen it. 2 plus 1, 2 plus 1, and 5 plus 1 times 4 plus 1 will just raise the exponents by 1. So 2 plus 1, 2 plus 1, 5 plus 1, 4 plus 1, and then just multiply it out. and you will get 3 times 3 times 6 times 5, so that is 9 times 30, and that is 270. So the number of devices of n is 270, and that concludes our given problem. So if you actually see, if you were well versed with LTE, this would be pretty easy for you. It could very well directly, because we had primes in the question, you could very well directly see that it could have been done by LTE. And in general, LTE is a really good technique to solve some of the more rigorous problems in number theory. So you should be knowing about it, and I hope you learned a little bit from here. Okay, so we have some book suggestions for USAMO, JMO, and AIME. Elementary Number 3 by David Burton. Problems on strategies by Arthur and Gell. Functional Equations by Venkatachala. Problems in Plane Geometry by Sharagan. Elementary Number 3 by Sierpinski. Graph Theory by Harari. And of course, Combinatorics by Brualdi. So okay, we have a similar but challenging problem, and again over here you just need to apply this concept of P-adic valuations on the LTE lemma, and it states that does there exist a positive integer n so that n has exactly 2000 prime divisors and n divides 2 raised power n plus 1. A beautiful question. I believe this is an IMO problem, so maybe try it out, and if you're able to do it, let me know. Until then, I'll see you in the next video. Thank you very much, and bye bye.
Cheenta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.